Hey, Algebra 2. This is lesson 812 from chapter 8. So we're going to continue predicting how we can create the equations of polynomials from graphs and also create graphs from the equations. So we're going to go ahead and get started. We're going to do some together, and then I'm going to have you guys try some on your own and check your work with my notes, my PowerPoint notes that I uploaded to each of those folders. So this is week 1, no, sorry, the second lesson from chapter 8, which is in week 3. So check those PowerPoints for the answers. All right, so today we're going to clarify and expand on some of the ideas that we learned from lesson 811. What is the maximum number of roots that a polynomial of degree 3 can have? The max roots would be 3. And the reason for that is a degree of 3 means that it could have 3 different factors, or maybe 2 different factors, but one of them bounces. And so an example could be maybe we have y equals x minus 1, x plus 2, and x minus 3. So this one would have roots at x equals 1, x equals negative 2, and x equals 3. So that'd be 1, 2, 3 roots. What do you think is the max roots, or the maximum number of roots a polynomial of degree n can have? So that would be, for any number, it would be equal to that number for the degree. So the max roots is n for degree n. So no matter what number of degree we have, the maximum number of roots has to match that degree. But it could also have fewer than that many roots. Under the condition, like I was saying, the double roots. If a polynomial has a double root, or bounces at that root. All right, so like, for example, if we had y equals, let's change that to x minus 1 squared, and maybe we have an x plus 2 still, that equation would bounce at 1 and then go through at negative 2. So it looks something maybe like this. So you see it only has 2 roots, but it has a degree of 3. Remember, the degree represents the number of factors, or it represents the highest exponent of that polynomial equation. All right, and so that 2 counts for 2 factors, even though they're the same factor. And then this one just counts for 1. So that's 2, 3. So that's why it's a degree of 3, but only has 2 different roots. All right, and this is one where I'm going to do number 1 with you, and then I want you guys to predict the minimum degree each equation can have, and I want you to check that on my PowerPoint that we did in class. So check your predictions. So number 1, the way that I figured all of these out was I made a line that represented the x-axis. So I made that line through here. Not great, but it shows you where the roots are. So there's 1, 2, 3 different roots. So this would be a degree 3. even if I made a line up here. This is a bounce, so that counts for 2, and that goes through, so that counts for 1. So it'd still be a degree of 3, even if I moved my x-axis up there. All right, so I want you guys to do the same for the second, third, and fourth graphs, and check your work on my PowerPoint. All right. So positive and negative orientation are important when writing the equations. So for positive orientation, that's when the leading coefficient in the front is positive. All right, oops, meant to get the highlighter there. And so I want you to write that down. Leading coefficient, so the number in the front is positive. And that's in the equation. And when it has negative orientation, that just means that the leading coefficient is negative. So I kind of remember this from our quadratics unit. If the leading coefficient was positive, then our graph opened up. And if the leading coefficient was negative, then our graph opened down like a frowny face. All right, and so to tell those apart, we want to look at for positive when the y values of a graph get very large as the x values get large. So I always look at the very last arrow on the right. So that's the last arrow is always when the x values get larger. Okay, so in both of these, we're looking at when the x values are at its largest, what happens to the y values. So in this first graph, since it's opening up, that means that it is positive, so it's going from negative to positive overall. So that would be a positive orientation. So graph 1 would represent that. So in the equation, we'd have like a positive number in the front. Whereas in graph 2, that's opening down, so that would be negative orientation. So in that equation, we might have a negative, or we will have a negative number in the front. So that one would look more like y equals negative x squared instead of positive x squared. All right, and then for graph number 3, we have positive orientation overall. And then for graph number 4, it goes from positive to negative. So overall, it has negative orientation. And again, that's just to help us when we're making our equations. All right. And so then consider the graphs of y equals x minus 1 squared and y equals x minus 1 to the 4th power. Y equals x minus 1 squared is a little bit narrower, and then y equals x minus 1 to the 4th power is a little bit wider. They both have x-intercepts at 1, 0 because of that root. It's both x minus 1, so they both have a root at 1. So I can go ahead and kind of sketch a graph right here where that's 1, and then that's also 1. All right, and they're also the same shape, so they're both a parabola. It's just that the difference is this one is a little bit wider than x minus 1 squared. All right, and then in part B, it's kind of the same difference. They are both going to go through 0, 0. So they're both going to have the same intercepts, and they're both going to have the same shape. It's just that when the exponent gets bigger, where it crosses, it gets a little bit wider. All right, so both have an x-intercept at 0, 0, same shape. It's just that this one is a little bit wider at the x-intercept. All right, and if you notice, when we have an even degree or even exponent, it bounces at that x-intercept, and they both have the same end behavior. They're both pointing up. Whereas when we have an odd exponent, like 3 or 5, they have different end behaviors, left or down and then up, down and then up, and then it also crosses at that x-intercept. Which brings us to number 30. When we have a double root, then it's going to bounce at that root. When we have a triple root, it's going to actually cross at that root. So we just remember those differences from before. Oops, wanted to use just like a black marker. So there's a bounce with that double root, whereas with the triple root, it crosses. It also kind of curves. Okay, and that's how the graphs look different. So this one would be a bounce at x equals -5. Whereas if we had x plus 5 to the power of 3, then that would cross at x equals -5 at kind of like a curve. All right, number 31. I'm going to graph all of these for you, and I would like you to write the possible equation for each of these graphs. I'll do the first one with you, and then I want you guys to try the other 3 on your own, and then check with my answer key from this PowerPoint. All right. So in all these, I'm going to go through where I'm going to bounce at the numbers they give me. But if the graph is bolded, I'm going to go above the x-axis. If the graph is not bolded, I'm going to keep the graph below. It's like on part A. I'll start below, and then I'll come up, and I'll come down, and then I'll come up. Okay, the reason for that is because not bolded on the left side, bolded on the right side. So that arrow is pointing down, this arrow is pointing up. This is bolded between -3 and -1. So I'm going to go above, not bolded between -1 and 4. So I'm going to go below. So I'm going to do this real quick for the other graphs. The important point of this is that you guys can kind of guess or predict the equation given the graph. And I'm not doing the greatest with these graphs right now. All right. Okay, so for this first graph, my equation is going to be something like y equals, since it goes through -3, I'm going to have a factor at x plus 3. It goes through -1, so I'm going to have a factor of x plus 1. And then it goes through 4, so I'm going to have a factor at x minus 4. And if you notice, I have 1, 2, 3 factors, and it kind of matches our x to the power of 3 graphs. So it goes below and then comes back up. And I know that it's positive orientation based on that second slide that we talked about. So I don't need to change anything in the front because it's already positive. If it were negative orientation, like in part D, I would want to add a negative to the front of my equation. So I would just like this, I would just put a negative in whatever I had already put for my factors. Since part A is not negative, I won't put that. I'll do B, and then I want you guys to try part C and D. So for part B, I would write y equals, and then use all my points to create the factors. There's a point at, or a root at -5. So I have one factor of x plus 5. There is a root at 0. So I have a factor at x, so I'm going to put that in the very front. You could also do x plus or minus 0 if you forget about the x in the front. And then I have a root at 2, which means I have a factor of x minus 2. Since these two roots are bounced at the graph, so they bounce off of the x-axis, that means that those two factors are going to have a square. So this should be squared and this should be squared. So my overall equation is y equals x squared plus times x plus 5 times x minus 2 squared. You don't want to forget about those. Okay? So you guys try C and D and check your answers with my PowerPoint. All right, number 32, I filled in the notes for you guys. So an even degree has graphs that kind of look like this. They could also kind of look like the W's that go up or the W's that face down. These are second degree polynomials. This one is negative since it faces down. These would be like fourth degree polynomials facing up and then a negative in front, negative orientation. These are our odd degree polynomials like x to the power 3, or if we have 3 factors, this one would be just a negative, just put a negative in the front, your leading coefficient, negative x to the power 3. It'll let me write a 3 on here. And then we could also have graphs that kind of look like this, where it's still x to the power 3, but it's going to be 3 different exponents, or 3 different factors is what I mean, 3 different factors. All right, and those are our notes for 812.